Hello everyone, today I'm going to present the work Incentive Mechanism for Reliable Federated Learning, a joint optimization approach to combining reputation and contract theory. The work has been proposed by Kang in 2019. I will give a quick introduction and motivation of the work, some background knowledge such as federated learning, system model, adversarial model, and why more detail about the work, evaluation method, and conclusion. As you guys may have heard about federated learning, for example, federated learning in designing a virtual keyboard application keyboard from Google. So what is federated learning? A machine learning technique in a distributed model training using local datasets from large-scale node, mobile device, but share only model updates without upload the raw training data. Why do we need federated learning? Because it provides privacy preservation for mobile device while ensuring high learning performance. Objective of the work, they focus on the worker selection and incentive mechanism issue for reliable federated learning in mobile networks. About the motivation for the work, most existing works focus on designing advanced learning algorithms with aim to achieve better learning performance, learning time, or training security in federated learning. However, the majority of the work make the same assumption that all the mobile devices contribute data, communication, or computational resources unconditionally for the federated learning. However, the challenges such as incentive mechanism for participating in training and worker selection schemes for reliable federated learning have not been explored yet. These challenges have hindered the widespread adoption of federated learning. In federated learning, each mobile device obtains a shared global model from a task publisher and trains the model over its local data. Then the mobile device uploads the new weights or gradients to the task publisher for update the global model. In global, the task publishers updates the shared global model to a weighted aggregation of all the local model updates. This is the overall of the method, including two layers, application layer, blockchain layer. The application layer we consider a universal mobile network consisting of wireless communication infrastructures and a set of mobile devices. The widely deployed communication infrastructures can be treated as edge nodes. In mobile network, multiple task publishers with federated learning tasks execute model training based on these data for mobile devices without data collection for the sake of privacy protection. Step A task publisher design contract items for incentivizing reliable mobile devices acting as worker for mobile training. Step B.C.D. Every worker iteratively train a set global model by its local data and generates local model updates. Step A. All the workers upload their local models updates to the task publisher for the updating global model. In blockchain layers, the training process is repeatedly until the accuracy of the global model achieves a predefined desirable value. The widely distributed edge nodes enable the workers to communicate with the task publishers in a timely fashion. The task publisher evaluates the quality of the local model, updates, and generates the reputation opinions for the interactive workers according to their model updates and training behaviors. The reputation opinions are maintained by consortium blockchain named Reputation Blockchain with the property of the tamper-proof and non-repudiation and are shared among the task publisher. Due to the openness and complexity of mobile network architectures, mobile device acting as worker may perform malicious or unreliable model updates. There are two types of malicious worker, intentional and unintentional malicious worker. However, as a result, both the intentional and unintentional behaviors degrade the local data quality and local model update quality, therefore negatively affecting the accuracy and conversion time of the global model. Therefore, it is essential to design a reliable worker selection and scheme for federated learning. A quick introduction about blockchain and consortium blockchain for those who don't know what is blockchain. Blockchain is a glowing list of records called a block that are securely linked together using cryptography. Each block contains a cryptographic hash of the previous block, a timestamp, and transaction data. A block each contains information about the block previous to it. They form a chain. There are 4 types of blockchain structures: public blockchain, private blockchain, and consortium blockchain. Consortium blockchain is more efficient, practical blockchain technology with a lightweight and fast-state consensus process controlled by pre-selected miners. Therefore, the consortium blockchain is especially suitable for reputation management in mobile network with federated learning. Reputational-based worker selection scheme with consortium blockchain including 5 steps. Step 1, task publisher, public federated learning task and contract item. Step 2, calculate the candidate reputation. Step 3, select workers for federated learning. Step 4, perform federated learning and evaluate quality of the local model updates. Step 5, update the reputation opinions to the reputational blockchain. We calculate reputation using the multi-way subjective logic. Subjective logic is a widely adopted framework of probabilistic reasoning that evaluates the trustworthiness or reliability level of different entity. Opinion or subjective belief can be positive, negative, and uncertainty statement. In this work, it can be belief, disbelief, and uncertainty. We calculate the reputation opinion based on the subjective logic model. And at the step B, we weigh the reputation opinion from recommenders. That means we weigh the publisher. Similar to social network, the more commonly interacted workers between 2 task publishers bring larger credibility of indirect reputation opinion for them. The indirect reputation opinion from different recommenders are combined into the overall recommended reputation opinion according to the corresponding weight of each task publisher. At the end, we combining direct reputation opinion from the step A and recommended reputation opinion from the step B. After we have the reputation for each workers, we build the incentive mechanism for reliable federated learning. An incentive mechanism motivates the high reputational workers with high quality local data to join the model training. By high quality data, that means high accuracy and reliable local training data. A task publisher offers a reward to the high reputational workers that make the contribution to federated learning tasks. We will define the profit function of the task publisher, unity function of workers, and the optimal contract design. To attract more workers with high-quality data, we define a parameter about data quality at the type of the workers with the denoted theta n. Here, the psi is a coefficient about the number of the local model interaction affected by the local data accuracy. For different workers with different computational resources, for example, CPU cycle frequency, the type publisher provides a contract including a series of resources at work to bundles to the worker. Here's Fn is the computation resources, type n workers, and Rn is the corresponding rewards of the workers. The more computational resources contributed by the workers lead to the faster model training, thus bring the higher reward. The objective of the task publisher is to maximize its profit in the federated learning task at the function 15 FLO. Utility function of workers. Intuitively, the higher type workers have a larger utility since they provide better quality data. Poisoning attacks launched by malicious workers degrade their local data accuracy, thus affecting the quality of local model updates. With the help of contract theory, the malicious workers will not choose to sign the contract items higher than their type due to individual rationality, ER. The worker wishes to minimize the energy consumption when performing the federated learning task for maximize its utility, as defined at the function 17. To optimize the profit function of the task publisher and unity function of workers, we need to define the optimal contract design. In the case of information asymmetry, we to make the contracts feasible, each contract must satisfy the following constraints: the individual rationality and incentive compatibility. In order to ensure that a type of the workers is fully motivated, individual rationality, that means every worker only participates in the federated learning task when the unity of the workers is not less than 0. Incentive compatibility, to maximize the unity, every worker can only choose the contract design for itself. That means the type θn instead of any other contract RMFN. The optimization problem in the equation 15 and 17 now can formulate as a optimization problem in the equation 35. To evaluate the method, they simulate a simulation problems using teacher's classification dataset, MNIST, and software environment TensorFlow 1.12. The MNIST dataset contains 16,000 training images and 10,000 testing images. They simulate 20 task publishers, 19 well-behaved workers, and 10 unreliable workers, with 8 workers unintentionally unreliable updates, and 2 malicious workers launching poisoning attacks. Specifically, well-behaved workers receive a training dataset following the uniform distribution over 10 classes. Unreliable workers only receive a certain number of classes randomly. Malicious workers with poisoning attacks receive a dataset with some label of the training example are deliberately modified to mislead the global training. To qualify the data quality of the local training data in the unreliable workers, they use the Earth movers distance (EMD) as an index. For reputation calculation, 15 honest task publishers and 5 compromised task publishers. The compromised task publishers provide fake recommended reputation opinions to other task publishers for misleading the reputational calculation. Figure 2 shows the accuracy of federated learning tasks under different data quality levels and the type strengths. Figure 3 shows reputational values of unreliable workers. Since they are unreliable workers, we want it to be low. And the proposed method, reputational scheme with the blockchain showing the green color, maintain the lowest value over other method. Figure 4 shows the accuracy under different reputational thresholds of successful detection. The proposed method, the blue bar, shows the best accuracy. Figure 6 shows the profit of the task publisher and the different total number of worker types. The proposed method in the dark blue bar shows the highest profit of task publisher. In summary, this article focuses on worker selection and incentive mechanism issue for reliable federated learning in mobile networks. Firstly, they introduce reputation as a fair metric to select reliable workers to defend against unreliable model updates. Secondly, they utilize multi-way subject logic model to efficiently calculate the worker reputation and manage the reputation in decentralized manner through the consortium blockchain. Third, they design an effective incentive mechanism using contract theory to stimulate high reputation workers with the high quality data to participate in model training in order to prevent poisoning attacks in federated learning. The result confirms that the contract-based incentive scheme can attract more high reputation workers to ensure reliable federated learning and optimize the unities about the task publishers and the worker. This is the end of the reputation. If you have any questions, feel free to leave the comment below.